Today we're going to talk about transformers. Again, this applies to both 126 and 140, so you're getting double your value here, although technically this is a 140 lecture. And we've already talked a little bit about transformers, so the one that I put up is a little bit more complex than the ones that we've talked about before, and we're going to look at a few more of the details this time that we've never looked at before. One thing that I've shown is that we have a primary over here on the left side with 20 volts of AC, and that's 20 volts RMS. And this particular transformer has two secondaries, not just one, but two secondaries. Okay, so if that's the case, let's look under the microscope and see what happens here. Because one thing that you might notice is I've intentionally drawn this backwards. These two coils, these two secondary coils, are backwards from each other. Do you notice that? Do you notice that this one goes around this way and this one goes around that way?
Oh.
You see how they're backwards from each other? So here's what we're going to do.
Wow.
We're going to come up with a quick and dirty way to determine how this works. And we are going to follow the direction of the current going from plus to minus. This is the way our current flows, right? Mm-hmm. And we're going to use our hand and we're going to follow that current around. So looking at this, the current flows in this direction here, going around that core. And my thumb is pointing in this direction. Therefore, we're going to write the magnetic energy going through the core in this direction. And I'll just use another Greek letter phi to represent the magnetic energy going through the core, the flux, the changes in the magnetic energy. Follows my thumb. When we go around the circle, what we see is the thumb pointing down, and now the thumb pointing down causes the current in the direction of my fingers. Okay, on the other side. So the current now is going in this direction, which means it's going from plus to minus, and I'm going to have plus minus current here. Okay, and my voltage, if this is 20 volts AC, and I have a 10 to 2, that's a 5 to 1 ratio, which means I'm going to have 4 volts out here. Right? 10 to 2 is the same as 5 to 1. For every 5 volts here, I will have 1 volt there. That gives me 4 volts. Okay? In the bottom one, thumb still represents the direction of the magnetic energy, but now when we look at how our fingers rotate, we see that the current is flowing this way, which means I will have 2 volts plus minus. Or negative 2 volts with plus on the top and minus on the bottom.
Is that 28.28?
Yeah.
Okay.
So this is our source voltage. Now we're representing it as 28.28 volts peak because this is 20 volts RMS. 20 times 1.414 is 28.28. This is 4 volts RMS. 4 times 1.4 is 5.6 roughly. Is that about right? And the other one here is 2 volts RMS. 2 volts RMS is equal to how much peak? 2 times 1.414 is 2.828 volts. Okay, questions?
Yeah, why is that coil, why is it +2 or -2 volts?
Well, the way we have it indicated here, before we even started this, we decided that the voltage was going to be this way.
Oh, because it's...
We made an assumption that the voltage is going to be this way, and if this is my positive terminal, and it says positive on the terminal itself, when I measure it, I'm actually going to get -2 volts because it's actually polarized in the opposite direction.
Yeah, it's wrapped the other way.
Oh,
It's wrapped the other way,
okay.
right? See how this is wrapped in the other direction? That means the current reverses. This one, current flows from plus to minus. In this case, current's flowing from minus to plus, which means you're going to get a negative voltage.
The left-hander did that one.
Yeah. Okay, so in a normal transformer that doesn't have this situation, we would use something called phase dots. And we're going to put those phase dots on here just to show you how that works. And in a schematic drawing, I would put a dot here, a dot here, and a dot here. And that indicates that these two are in phase with each other, which is the two that we're showing there, and these two are out of phase with each other, which is as we're showing it on there. So we have something called phase dots. A lot of times in a schematic, what you would see is you'd see something like this. And that indicates that when this is positive, this one's negative, they're out of phase with each other. Okay, any other questions? I need to make some room. Are you ready? You need to copy anything?
I need to do that transformer that you just put up right there, so.
All right, well, I'll get
Leave
busy
that for just a second.
getting rid of some of the other stuff then.
Okay, you can get rid of it.
Oh, I broke some of my coils. Just want to get rid of some of the junk that's in here. And I want to talk a little bit more, again, looking at the microscopic version of what's going on here. Have you ever looked at Google Earth?
Ever looked at what?
Google Earth.
Yes.
You ever see racetracks from the air on Google Earth, like horse race or car race tracks? Usually when we see something like a racetrack, looks like that? Why doesn't it look like this?
Because they don't have corners, they run.
So your answer is they look like that because they look like that.
Well, the tracks themselves are oval, they're not square.
Why?
It'd be hard to turn, and also maybe to use more surface area.
Yeah, because the velocity they're going,
More
right?
surface area.
It's surface area they don't need in a square.
Well, surface area does a racetrack. It does. Nobody cares about efficiency in a racetrack. These cars get like a half a mile to a gallon. Nobody cares about being efficient. But I think somebody had commented that it's hard to make turns around corners.
Yeah, you don't need squares.
You know, well, it's independent of whether you need it because it could be more of a challenge,
Yeah.
couldn't it?
Mm-hmm. Too dangerous.
But yet, when we design highways in order to maintain a certain flow of traffic, one of the things that they talk about with highways is the radius of the turn. Okay, when you have a highway, that highway has to have a certain radius of a turn to support the centrifugal force of a car going at the speed that it's going around it. Okay, that radius is important. That goes into the design. When they talk about something called dead man's curve, what do you think they're talking about? They're talking about a turn that's too sharp to support the speed of the traffic going around that turn.
Yeah.
Well, you know, that's all great that we talk about that, but what about this situation? One of the things that we've stood by since we first started talking about electronics and electricity in general is that voltage times current going in is going to be equal to voltage times current coming out. In other words, the power in the primary is equal to the power in the secondary. It has to be. Conservation of energy, conservation of matter mandates that that be the case. But yet, even the best of transformers is not apparently true. I will not get the same multiplication as I get here. It will always come out less. In other words, my electrical power out will be less than 100%. And the reason for that is just what we were talking about. Okay? Earlier we drew a nice convenient little oval that represented the flux, the magnetic flux that was flowing through our transformer. But that couldn't be further from the truth. Here's what's actually going on. Imagine this being water. Imagine water flowing through around this circle. It's being forced through here and coming back here and getting pumped back around in this circle. What do you think you're going to see? Well, you're going to see this. Get rid of these dots because they're really not there. You're going to see this. Yes, you will see a component of energy flowing in a circle. But what you're also going to see are whirlpools. You're going to see an inefficiency of that energy. All of the water is not going to move. Some of the water is just going to sit there. Just go around in a circle. Right? Okay? These are called eddy currents.
Haven't heard that one in a while.
Yeah, I was going to say that's been a while too.
The solution to eddy currents is to do this. make a round transformer.
Toroidal.
Right, use a toroidal transformer.
I'll probably never forget that word.
Yeah.
When we played that game that one day, that was on the test, and I'd never even seen it or heard it. And I'm sitting here looking down and going, well, okay, that's got to be the answer because the other ones didn't fit. And like the time I went to write my answer down, that question came up in the game.
Oh, yeah.
And it was like, Robert, number 4.
Yeah.
We just got the answer out of that.
There you go. Whatever works, right?
Yeah.
You'll notice I put some dollar signs up there because toroidal transformers are expensive to make. It's harder to make stuff circular than it is to make it round. So, you know, normally toroidal transformers are made by making a powder and then casting it into a mold, making a nice round little donut that we wrap the wire around. And when we do that, of course, then the lines of magnetic flux can pretty much run unimpeded around that toroid. Okay? Can I get rid of this big drawing for a while? I'm tired of looking at it. What I want to do is I want to turn this transformer sideways. And I want to look at it like from an end view. And if I look at it from an end view, what I'm going to see is basically this. I'm going to leave some of the coils out. I don't need to draw all of them. You understand what that means? Why X's are here and dots are there. It's something that you see every now and then. You might never see it again from me.
Protons, neutrons?
What is it?
Protons, neutrons?
No.
No?
Is it the PN junction?
No, there's no PN junction here. It's way simpler than you think it is.
Oh, what's that thing called?
Input output? I don't know.
It's a wiring connection. It's like a cannon plug.
Here's an arrow. What does that arrow look like from the back? Doesn't it look like this from the back?
Oh, yes.
Because those are the fins of the arrow as it's going
Oh,
away
as a
from
target?
you. And then when you look at it from the front, you see the head of the arrow with a dot in the middle representing the point. So this represents going that way. This represents coming this way. So these are the coils. And
Okay.
It comes in this way, goes around, around, around. You see how that is? See how I'm trying to make a three-dimensional representation in two-dimensional space is somewhat challenging at times. But the general idea is when I have this coil wrapped around that core that I'm going to get magnetic flux, maybe from, goodbye, oh, almost, so close. I'm supposedly going to get magnetic flux flowing in that direction. Okay? But if you ever been to China, have you ever been to China? Have you been there?
Japan.
I don't think
Never
Japan's
China.
quite the same as China.
No.
In China, they have roads that have everything from semi-tractor trailers to people on horseback and pulling carts and everything
Man.
else. And they're on the same big, wide road.
Sounds like
and
Korea.
There's no lanes. It's just a big dirt road. It's a huge, wide road, and you've got these trucks barreling along, and you've got people pulling rickshaws along on the
Wow.
same road. And what you get when there's no lanes is you get people that are just kind of meandering around from place to place, you know. There's really no organization. And if you have people that are bouncing off the corners and edges of the of the roadway. Yeah, I'm going to stop over here and talk to Bob, and then we'll get going. You know, just make a pull over, you know, block people in. What ends up happening is traffic doesn't flow very well.
Right.
Does it?
Nope.
And so what we normally do is we establish lanes of traffic, like so, that force the energy to go in a straight line, or force the cars or vehicles to all go in a straight line. Okay? We have the same problem with transformers. Transformers have a hard time with this. So what we do when we build transformers, I'm looking for an example around here, because none of these actually show it. But when we make transformers out of laminations. We'll take a flat piece of steel, put an insulator in between, another piece of steel, another insulator, and we'll layer our transformer coil or core to force the magnetic flux to flow in straight lines. I did have one. I don't know where it went. Oh, maybe over here. No, this one you really can't see either. I had a demo sitting around here, a transformer that was half taken apart and appears to have vacated the premises.
Installations.
There's one on my computer. That's an old transformer.
Is there?
I don't know if that's what you're looking for.
Yes, perfect. Thank you. Yeah, I've been looking for this for a while. What happened to it?
It turned up during our cleanup day, and I was looking at it. You're lucky it was on the go-away table.
Oh, was it?
It was. I thought it was cool looking in. I thought, he collects these. I'll bet he doesn't want this going away. That's why it's on my computer versus home.
Yeah.
Let's see if we can get any picture. Come on. Today. There you are. This is like one out of Frankenstein movie type deal. But there you can see the laminations. That's one of the things, one of the reasons I like to keep some of this old crap around, is because it does show you things that they hide in the new ones. Okay, so there are your laminations.
So basically, transformers are still the same. They just hide it inside of a case.
Well, you know, yeah, they hide it inside of a case. The thing that you have to recognize is that all of these problems that we have with transformers, the eddy currents and all that, we've already said that the power in is not equal to the power out because of it, but we also know that the power in has to be equal to the power out because of conservation of energy.
Right.
So what that means is part of the electrical power that's going in is converted to heat.
Okay.
Right? So when you have these laminations, you'll notice that there are gaps between, there's air gaps between those laminations in these older transformers.
Okay.
That allows the transformer itself to express heat and to remain cooler. Okay, now with the advent of plastics and other types of materials, they don't need to do that as much anymore, and a lot of times these things will be like the ones that you see over here, completely sealed up and potted. And actually, out of the corner of my eye, I already have another one of these.
So they're making the transformer out of different material?
Oh, everything's made out of different material now than it was in the 40s. If you look at this other transformer right here, this one, if you look at the plastic that's made up, you notice it's already cracked on the bottom.
Yes, sir.
This is made out of something called Bakelite. This is plastic, the very first type of plastic that they made. It's a whole lot different than this type of plastic that we make nowadays.
Yeah.
Bakelite was very brittle.
Yeah, I was gonna say, I can remember mounting some components that had plastic bases, and you had to be real careful.
Yeah, it has no give at all. It's
Yeah.
very brittle.
Yeah.
It's not like PVC or
Yeah.
the plastics of today
Yeah.
that have polyethylene and stuff in them that give them some pliability. This stuff has no pliability at all.
I had taken apart my power amp in my JVC, and that joker had, I looked at the transformer, my circuit board was cracked, so that's why it wasn't working right. But then when I looked closer at the transformer was cracked. Come
Well,
on.
I think you figured out what's wrong.
Man.
Okay, I'm going to go ahead and cut off the video because we're going to go through this problem. It's not part of today's lecture, so bye.